Okay, so we're going to talk about the energetics of the solution process with this and get you thinking about charge density. But first, suppose you had the positive side of a magnet stuck to the negative side of a magnet. All right? So what do you have to do to break that attraction between the two magnets over here? What do you have to do? You have to grab a hold of each end and you pull. You pull them apart because there's an attractive force, and to break that attractive force, you have to absorb energy into the system. You have to pull those magnets apart. If the magnets are close enough to have an attraction between each other, what do you do to make them come together? You let go and they will snap together. And at that point, energy is being released because the energy of the system becomes lower as the attraction is formed. So when they're stuck together, we have to add energy to break them. When the magnets come together, energy is released. That's exothermic process. Now bonds, chemical bonds, are kind of doing the same thing. When you have two particles or two atoms bonded together, it's at a lower energy than the two atoms separated. And the reason is because the electrons of one atom are attracted to the proton of the other atom and vice versa, and you get a stable chemical bond formed. So if you want to break that bond, you have to add energy. That is an endothermic process with a positive delta H. We'll tell you why that's positive in a little bit. All right? So if we have a chemical bond, we want to break the chemical bond, we're talking about an endothermic process. Energy is absorbed. Whereas if you have two atoms coming together to form a chemical bond, energy has to be released. This is of lower energy. The product is of lower energy. The bond formation is of lower energy than the two atoms separated. So when they come together, energy is released, and that is a negative enthalpy, minus delta H. Now, what are the energetics of the solution process? Well, you got three things to worry about. First, you have attractions between the solute particles, what we call solute-solute attractions. And we want to break those attractions. Since we're breaking attractions, that's going to be what? An endothermic process with a positive delta H. So that's the first thing. We have to separate the solute particles. The second thing is the solvent particles also have to be separated. And that also is an endothermic process. Energy has to be absorbed to do that. But finally, the energy payoff comes when the solute particles, now separated, and the solvent particles, now separated, mix. And what happens? The solvent surrounds the solute particles, attractions are formed, and energy is released. So this process is going to be exothermic. So it's the interplay between those three that determines whether the overall solution process is exothermic or endothermic. So here it is mapped out on kind of a graph. You've got enthalpy right here. And what happens? We take our solute, which is all stuck together, and we separate them. And that is climbing uphill energy-wise, and energy is being absorbed. We take our solvent particles stuck together and we separate those, and that too is endothermic. But finally, the energy payoff, where the solute and solvent particles form attractions with each other, and that is all exothermic, and energy is released. Now, enthalpy is a state function. It means that you're unconcerned with the path all you need to worry about is the energy of the reactants and the energy of the products. And if the products are of lower energy than the reactants, then you have an exothermic process. And this is the energy that's released in this. In other words, when this solute and this solvent are mixed, in this scenario, there's going to be energy released. If you touch the mixture, it's going to feel warmer than the, say, the water before you mixed it. Okay? Whereas, if these two energies are greater, the two energies of separating solvent particles and solute particles are greater than the energy you get from mixing solute and solvent particles, then you're going to have an overall endothermic process where energy is going to be absorbed. And you touch that solution, it feels colder. So that's the energetics of solution. And if you take a look at various salts and putting them in water and dissolving them and watch what happens to the temperature, almost all of them are exothermic. But look at sodium sulfate. As the solution forms, it actually gets colder. So that's an anomaly compared to the other salts. Now, the one thing that we haven't talked about that is on the homework and is the reason for this video is charge density. It's not covered in the book, and that's why I wanted to touch on it on this video, because there are a few questions on charge density and heat of hydration, because it relates to solubility. The charge density is a ratio of the charge of a particle, that's +1 or +2 or +3 or -1 or -2 or -3, the charge divided by the size of the particle, the volume of the particle. So if the charge is large and the size of the particle is small, then you're going to have a high charge density. If you increase the charge, you increase the charge density. If you make the volume of the particle smaller, you get a higher charge density. So charge density is the charge of the particle divided by the size of the particle. The larger the charge density, the greater the heat of hydration. And why is that? Because of Coulomb's law, you get more energy when you have a higher charge density on the particles that are being hydrated by water. So let's take a look at neutral atoms versus their ionic forms and take a look and see what happens to them. If we look at sodium, it's 186 as a neutral atom, and it's 102 when it's a +1 ion. Or magnesium, it's 160 as a neutral atom, it's 72 as a +2 ion. And aluminum really shrinks from 143 to 54. So when we form positive ions, the ionic size is smaller than the neutral atom. Conversely, if we take a neutral phosphorus and we add 3 electrons to it, it more than doubles in size, going from 110 to 212. Or sulfur, we start at 103, we add 2 electrons, it goes to 184. Or chloride, and chlorine, I start at 100, I get to 181. A negative charged ion is larger than the neutral atom. So, once again, positive ion is smaller than its parent atom. Negative ion is larger than its parent atom. So we get a question put in order of increasing charge density. And we have aluminum as a 3+, potassium as a K+, magnesium 2+, chloride as a -. Can you do that? Well, just think about it. Chloride has a size of 181, and it is a negative ion, a -1 ion. And its size is 181. Charge over size is the charge density. Potassium, K+, even though it is in the next period down, because chloride is negative, its ion size gets larger. Potassium giving up an electron gets a smaller ionic size. So the ionic size for K plus is 138. It's smaller than Cl minus at 181. And it therefore, since we're both talking about a -1 or a +1, the charge is the same. They're opposite, but the same in terms of Coulomb's law. But the size is the difference. The potassium ion is smaller and therefore has a higher charge density. Mg2 plus, magnesium ion is 72, right? Now we've increased the charge. We've doubled the charge of the magnesium ion. And that shrinks down, because we're making a positive ion, it shrinks down the size of that magnesium ion. So this is going to have a much higher charge density than K plus or Cl minus. And the winner of this, of course, is going to be the aluminum with a +3 charge in the numerator and a size of 54. And I want to say a quick word about gas solubility. You know, when you open pop, it fizzes and the carbon dioxide is allowed to escape. It is locked in the solution under pressure. And when we release the pressure, it comes out of the solution. And that accounts for the big fizzing that we get when we open a pressurized can or bottle. By putting it under pressure, we force the carbon dioxide to dissolve in the water. The water is able to form a few attractions between the carbon dioxide and water, and the carbon dioxide dissolves. But if you think about just opening a can of pop, when you get the most fizzing, you should be able to answer this question: which conditions most increase the solubility of a gas in a liquid? Okay, so we'll be asking you this question in class also.